Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we'll be going over series. So in my opinion, series was one of those topics where a lot of students struggled. So I feel like in this unit, you would need a lot of practice because the material has not been previously seen before. There's just a lot of problems that you haven't encountered in your mathematical career, as opposed to stuff like integration. Maybe you've seen it somewhere. Series, you generally don't touch until Calculus 2. So I would recommend doing a lot of practice problems and kind of reviewing the content whenever you can. So now on to series. In last lesson, we talked about the sequence, let's call it A of n, and then we would say, okay, well, it spanned from n equals 1 to infinity. And all this was just an ordered collection of terms, right, all the way to like A of n, and then we'd have some more, right? So all it was this ordered collection of terms, and they really had nothing to do like with each other, apart from that they were in the same collection. But now the series aspect of it is what happens when we try to add these terms and not just kind of separate them into some sort of collection. So in this case, we would get the series A1 plus A2 plus A3, and this would go all the way on to A to n, and then obviously we would add all the way up until infinity. So now we have learned about sigma notation previously, and we kind of know how to write this expression using sigma notation, basically compressing it using one mathematical symbol. And we can write this as, well, the sigma up until infinity from n equals 1 of A of n. Another way that we could write this series in this unit is just the sigma notation of A of n, because it's kind of common to have these bounds from n equals 1 to infinity, so we can just shorthand it and just write sigma A of n. Now this right here is called an infinite series, or just a regular series, and this is what we're going to be dealing with today, and we're going to be talking all about convergence and divergence of these series and a few other popular series that we're going to see all throughout this unit. So moving on to the topic of partial sums, we kind of know that the series will span from, well, it's usually from n equals 1 all the way to infinity. So it's going to be this large like addition of a bunch of terms, right? And a lot of the times we're interested, what does that actually come out to? What is like that final term? Once we add all of these terms, which happen to be infinite, what is the true value? Well, we can kind of use the idea of partial sums right here to compute that. And basically what I've wrote here is, since the series spans until infinity, meaning it goes all the way up until infinity, we want to use the notion of partial sums to get a sum up to n, and it's basically denoted as s of n, where n is like the nth term. So I've given a couple of examples here of what a partial sum might look like. So s of 1, meaning the partial sum up to 1, well, that would just be the first term of the series. The second partial sum, s of 2, would be the sum of the first two terms, and likewise for s of 3, where we basically just sum up the first three terms. And then we can write a general expression for the nth term. Basically, we would take the summation of all the terms up until n, and we can rewrite this kind of, again, using sigma notation to compress it down. So it basically just spans from I equals 1 to n, and we want to sum up A of I, meaning whatever I we're on, we want to just sum up all the terms up to n. So we can use these partial sums to kind of compute what the actual series sum will be. And again, we can do that by assuming that, well, since the series itself will span up until infinity, what if we want to compute s until infinity? So basically n is equal to infinity. And we've seen this plenty of times. We know how to set n equal to infinity, and that's kind of what we're going towards. We're basically going to take the limit of the partial sums to figure out the sum of the series. So like we talked about in sequence, we're going to talk about the same thing in series. And we always want to talk about convergence or divergence of a series. So what I've written here is that if the sequence s of n, we've seen this before, is convergent, and limit obviously exists if it equals some value, then the series given by the sigma of A of n is convergent. And otherwise, we say that the series is divergent, meaning we don't have that limit or the limit doesn't exist, whatever you want to say. In that case, the series will be divergent. So on to our first example, and hopefully you'll be able to grasp how we can use the partial sums to kind of figure out if a series is convergent or divergent, and basically the sum of the series at the end. So the example goes as such. It says, suppose that we know the first n terms of a series is given by this formula right here. S of n is equal to the first n terms, and we actually have an explicit formula for what the sum of the first n terms are. It's going to be 2n over 3n plus 5. And then the question asks us, is the series convergent or divergent? Again, the series will be convergent right here if the limit of the partial sums exists. And basically the reason we want to compute the limit of the partial sums is, well, S of n gives us an expression for the sum of n terms, but we want the n to equal to infinity. Because the series ranges from n equals 1 to infinity, we want to compute the sum of all the terms, basically from n equals 1 all the way to infinity. So we want to say that we want to compute the sum of kind of like this. This probably isn't correct notation, but that's essentially what we're looking for. We want n to equal to infinity. So since S of n is equal to 2n over 3n plus 5, what we want to do is we want to take the limit as n approaches infinity of this partial sum right here. We have solved limits similar to this all the time, so we know that this is just going to equal to 2/3. And again, because this limit exists and it's equal to a finite value, that would mean that this series right here, whatever it be, is actually going to be convergent. So moving on to this example, let's look at what we have here. We are basically given a series right here, and this question would be asking us for to find whether this is convergent or divergent. So we are given this series, and then we simply want to know, is the series convergent or divergent? Again, the way we're going to do this is we're going to find the nth partial sum, so S of n, and then we basically want to take the limit of it, basically setting n equal to infinity, and then seeing if that exists or it doesn't exist. So let's find S of n. Well, in this case, S of n is simply going to equal to a plus ar squared plus all of these terms up until arn minus 1. Now this equation right here doesn't give us much, to be honest. It's not really an explicit formula that we can take the limit of, so we are kind of going to need to find a workaround. What I'm going to do is I'm going to multiply r by S of n and get this kind of new formula. And now what I'm going to do is I'm going to subtract that new formula from S of n. And as you can see over here, if we subtract these two, well, these two terms will cross out, these two will cross out, this term will cross out. Basically, all the terms will cross out, except we'll be left with two terms. This one right here, and this first one right here. So all this expression right here is going to evaluate to is going to be a minus arn. And since we're solving for S of n, I'm going to factor out S of n to kind of isolate for it. And then on the right side, I'm going to factor out a. Now I want to solve for S of n, so that's going to equal to a 1 minus rn over 1 minus r. And so now we have an explicit formula for what S of n equals. And like we said, we want to take the limit of S of n as n approaches infinity. So that's going to equal to the limit as n approaches infinity of a 1 minus r to the n over 1 minus r. Now, what I'm going to do is I'm going to move the terms that are not dependent on this n value outside of the limit, so we kind of simplify it. So this will be equal to a 1 minus r times the limit of 1 minus r to the n. Now I'm going to distribute this limit in a sense, basically using limit properties. So there we go. Now I'm going to compute this limit right here. And now I'm going to move on to the left side of the page just so we have more space, but I'm basically going to redistribute this outer term right here. So we're going to get that a 1 minus r minus a 1 minus r times the limit of r to the n. Now if you remember from last section, we actually solved this limit right here, and we know that this limit, the limit of r to the n as n approaches infinity, is actually going to be equal to 0 if r is going to be in between -1 and 1. So let's assume that r is going to be in between these bounds, and then in that case we will have that we are left with a1 minus r minus a1 minus r times 0, which is just going to equal to a1 minus r. Now, we actually don't need to test all the other cases of r, because the only other case where this limit existed was r equal to 1. However, we can quickly see that the series of r equaling to 1 just won't really converge, because, well, this will be equal to 1, this will be equal to 1, this will be equal to 1, and we're basically just going to get this series is equal to n times a, and then the limit as n approaches infinity of n times a, well, that's going to equal to infinity, so this is going to diverge. So we don't need to check all the other possibilities of r again, because this limit right here is only equal to, like, it only exists if r is in between these values or r is equal to 1. But as we saw, r equal to 1 does not even work. The series is going to be divergent for it. So we just want to stick with this r value right here that we found. And if r is in between those bounds, well, then now we have that the sum of the series is equal to this value right here. That example that we just did, it's actually very well-known series. It's pretty popular, and we are going to come across it definitely in future lessons. So it's called the geometric series, and it's given by this formula right here. And as we found out, it's convergent when the absolute value of r right here is going to be less than 1. And its sum, the sum of the series, is going to equal to this expression, where a is this term right here, and r is this like rate. So we know that the series will be convergent if r falls within this condition, and it's divergent if r is going to be basically anything else but from -1 to 1, non-inclusive. So now in this next example, we are given this series right here and asked, is this convergent or divergent? I can clearly see that this is going to be a geometric series. If you can't yet, these problems are fairly common, and they're actually fairly easy to solve as well, so I would say to practice a few. Basically, what we want to do is we want to kind of convert this into what the geometric series looks like. So it looks like a rn minus 1, right? So we need this constant value of a, then we need some sort of rate, which is, again, it's going to be a constant too. It's going to be some sort of value, and then we want to have it to the power of n minus 1. So what I'm going to do is I'm going to manipulate the given series to look like that. And here's the way we're going to do it. First, what we want to do is we're going to try and get this n minus 1. So a quick way that I can do that is that I can say that this is equal to so the same bounds. I want to get n minus 1, so I don't need this 2n. So what I'm going to do is I'm going to use power laws and say that it's 2 squared to the n, and then on the 3, because I want it to be n minus 1, if I factor out a negative, I will get n minus 1. So now this series is looking promising, so I'm going to continue working with it to try and break it down into that form. So 2 squared is going to be 4 to the n, and then 3 is actually to the power of a negative. So that means if we like bring it down in a sense in the fraction, it will just become a positive. It's one of the power laws. So we're going to get something like this. And now we could see this n minus 1 here. We just need an n minus 1 here as well. And one way we can do that is by kind of removing a 4 from here. So it'll look something like, so we're going to remove that 4, and we're going to say that this is 4n minus 1 now. And then this will be 3n minus 1. I'm going to sort of merge these two right here together into one so that we get this single n minus 1. And you'll see how the series will come together. There we go. And finally, it looks in the format of a geometric series. And the question was asking us, well, is this series convergent or divergent? And we know that for a geometric series to be convergent, we need that the r, the rate, is going to be less than 1. And in this case, we can clearly see that 4 over 3, it's not less than 1, so it will actually be divergent. Moving on to another type of series, this is called the telescoping series, and it's basically a series whose partial sums cancel out to have a finite amount of terms. So as we saw before, we kind of did something similar in a sense over here, where we built these two equations right here, and then we canceled out these terms to only be left with these two terms. And so this right here really isn't an example of telescoping series, but I will give you a good example of how that same concept will be applied. So let's say we were given an example like this. We were asked to find whether this is convergent or divergent. So we'd start off by finding S of n. So what would S of n equal to? Now in this case, this is when you would want to use telescoping series, and you would kind of want to use the approach for finding what S of n is. If we were to just start off by saying, okay, well, S of n is equal to, I don't know, it's going to be 1 over 2, then plus, if n is 2, then it's going to be 1 over 6, and then so on, all the way up to n. Well, that really isn't going to tell us much. So we need to sort of manipulate what we're given here, this series, to find two kind of terms that will, in a sense, cancel out. And I'm going to show you how we can do that now. So we have dealt with these sorts of irrational functions back in integration by partial fractions. So it's going to be a similar approach. Basically, we want to split up this irrational function right here into a over n plus b over n plus 1, basically having these constant terms over every linear factor. And then we want to figure out what a and b are. We're going to be given this equation that a times n plus 1 is equal to, plus b of n. And now I'm going to simplify this a little further. So we're going to have a of n, or a times n plus a plus b of n. And this is going to equal to that a plus b times n plus a. Now this would be the expression for the numerator, and as we can see, the numerator is supposed to equal to 1. So we know that a plus b is equal to 0, and that a is going to equal to 1. If this seems foreign to you, I really suggest you go back to the integration by partial fractions video. I go over it a lot more in depth, and I go over a lot more scenarios, but this should be kind of review at this point. So we get that a is equal to 1, and that b is equal to minus 1. So now that we have these a and b terms, what we can do is we can substitute them in for this equation right here. So we're going to be given that it is the series sum from n equals 1 to infinity of, we said it was this that we were going to substitute in. So a is equal to 1, so it's going to be 1 over n. And then we're going to subtract away 1 over n plus 1. Now you can see how now we have these two sets of terms that are going to basically cancel out. So now let's go on to find what S of n is. Well, what is S of n? Let's take n equal to 1. Well, in this case, it's going to be 1 over 1 minus 1 over 2. Now, through the next iteration, n is equal to 2. So we get 1 over 2 minus 1 over 3. Now, how about another iteration where n is 3? So we get 1 over 3 minus 1 over 4. And we're going to keep on doing that. And then let's say we get down to n minus 1. Well, so we'll have 1 minus n minus 1. And then this will be minus 1 over n. And then I'm actually going to write the next term down here. And now, once we've hit n minus 1, let's hit actually n, because we're looking for the partial sum up to n. So we're going to say that this is going to be 1 over n minus 1 over n plus 1. So we've basically written out all of the terms from n equals 1 to n equals n. And this is going to be the sum of them. And the reason we've done this is to kind of get a glimpse as to what which terms we're going to be able to cancel out and which terms we're going to need to keep. As you can see, starting from this term, this one right here is negative a half, but we have a half coming right after it. So these two terms will be able to be canceled out. And then if you look onwards, we can do this with pretty much every single term. Here's 1/3, or minus 1/3, here's 1/3. We can cancel these two terms out. Here is minus 1/4. And you can guess that in the next set of brackets, we're going to be having 1/4 here. So we're going to cancel this out. Now, n minus 1 was probably somewhere here. Not probably, but it 100% was. So we can cross these two terms out. And then we get minus 1 over n. And then we get positive 1 over n. So we can cancel these two terms out. And finally, we reach this term. And we could see that the only two terms left that wouldn't be crossed out is going to be this 1 over 1 and minus 1 over n plus 1. So therefore we can simplify this partial sum to say that S of n is equal to 1 minus 1 over n plus 1. So now we have an expression for the partial sum, and like usual, we want to set n equal to infinity because we want to find the sum of the series when n is equal to infinity, basically the end of the series. So we're going to say the limit of s of n as n approaches infinity, this is going to be equal to the limit as n approaches infinity of 1 minus 1 over n plus 1. And I'm just going to go ahead and simplify this really quick. So there we go. I've used my limit laws and I figured out that the limit is going to equal to 1. Therefore, this series is going to be convergent because the limit of s of n, the partial sums up to n, exists. Another very popular series that we often come across is the Harmonic Series, and it's given by this expression right here. It's basically 1 over n, and then n spans from 1 all the way to infinity. And the important thing to note is that this series is always divergent. There are multiple ways you can prove it. One of the ways we can do it is through the integral test that will be coming up in future lessons. That is probably the easiest one, and it's the one that jumps in mind, but we kind of most people who work with series kind of know it's like almost a given that the harmonic series is divergent. So if you ever come across it, just know that the series is divergent and you don't really have to compute anything. So now going on to the convergence theorem trick. Basically, the convergence theorem states that if the series a of n is convergent, then the limit of that term a of n is actually going to equal to 0. Now, this doesn't really help us out much because in a lot of the questions, what we're looking to do is we're looking to find out if the series is convergent or not by using some sort of method. So this series just tells us, okay, well, if it's convergent, which is kind of what we're looking for, then this conclusion follows it. So that, in a sense, really isn't helpful. And it's the reason I've titled this the convergence theorem trick. It's because we're kind of going to apply a little bit of logic. I know that many of you probably haven't taken discrete math or some intro to propositional logic course, but don't worry, I'm planning on making it sometime down the line. But basically, this statement is an implication statement. We can see that if we have some, like, if something is true, if a condition is true, right? So if the series is convergent, then we see a conclusion. So in propositional logic, you generally write that as P implies Q, or meaning like if P then Q. But the thing about that is, as we said, this doesn't really help us. And we sort of can't just rearrange this and say that Q implies P. So we can't say that if the limit of a of n equals to 0, then the series is convergent. These two right here are not logically equivalent, so we can't do that. However, what we can do, and they are logically equivalent, is we can negate the conclusion, and then we can say that it implies the negation of the premise or like the condition. So we can say that not Q implies not P. Basically, that would translate to the negation of this. So we would say that if the limit, so if the limit, we want to negate Q, and negate Q was previously the conclusion. So the negation of this right here would be that if the limit of a of n as n approaches infinity is not equal to 0, then we want to take the negation of the premise or the condition. We want to negate this thing right here, so then we say that then the series is divergent, because that is the opposite or the negation of convergent. So now we have come up with this other little theorem in a sense, and this now is a lot more helpful because it will help us determine whether a series is divergent. Now, what we can't say, again, we cannot say that if the limit of a of n equals 0, then the series is convergent. We cannot say that. So don't get that mixed up. The only thing this theorem will help us with is that if the limit of the term a of n is not equal to 0, then the series is divergent. We cannot say the opposite. Let's say we are given this series right here. It basically, again, spans from n equals 1 to infinity. And then the term a of n right here is n squared over 5n squared plus 4. So I can clearly see that if we take the limit of this, it'll clearly be equal to 1/5. So if I say that the limit of, as n approaches infinity, of n squared over 5n squared plus 4, this is clearly going to be equal to 1/5, and that is not equal to 0. Therefore, we can quickly say that this is divergent. And you can see how helpful this trick is in determining the divergence of a series, because all we need to do is we literally need to look at this term and like think to ourselves, what will the limit be equal to? And if it's not equal to 0, well, then we can quickly apply this trick and skip a bunch of steps and basically just figure out that it's divergent. So like we did for sequence, for series, there's a very similar thing. It's basically convergent series, and it's, in a sense, it's a combination of two series and then basically state which ones are convergent and which ones aren't. So we want to imagine that we have two series, A of n and B of n, and then that they are both convergent. So then if they are, then if we take any constant multiple of A of n, it will also be convergent, and it'll be equal to this. And likewise, if we take the sum of both of these series right here, that will also be convergent, and we can see why. We're going to break it down into their individual series right here, and since both of those separate ones are convergent, then the whole sum is going to be convergent. And same thing applies to the difference. The difference can just be broken down again into their separate series right here, and since both of those are convergent, then the whole difference will be convergent. So moving on to our last example, the question asks us to find the series sum of the given series right here. And again, the series sum, all that means is we want to find what this entire series will be equal to if we were to add up all these terms. And we already know how to do that. We basically, like, if this is the partial sum right here up to n, but we want to find the series sum, we know that n ends at infinity, so in a sense we are looking for this, where s is equal to, or sorry, where n is equal to infinity. And again, the way we do that is we take the limit as n approaches infinity. So let's find what this series is actually going to be equal to. First, what I'm going to do is I notice that this right here is not a very common series, and I'm going to break this down using the laws that we have just learned into a much simpler series. There we go. I have used that sum rule, and I've split up the two series. Now what I'm going to do is I'm going to factor out this constant factor right here, again using one of those laws, and I'm going to simplify this series right here to make it look like a geometric series. Lastly, what I want to do is I want to make this right here look like a geometric series. So that would mean that we have this a, we would need some sort of a here, and then we would need n minus 1. So what I'm going to do is I'm going to kind of take out a term of 1/2, basically changing this to n minus 1, and because I've taken out that term of 1/2, I'll move it to the front. So there we go. Now we have two familiar series. And we have previously seen the solution for this series in the Telescopic Series example. So we know that it is actually going to equal to just 1. So we can write 3 times 1 plus, and right here we know that the series sum of a geometric series is given by the equation a over 1 minus r, where a is that front coefficient and r is that sort of rate. So we can solve this by plugging in what a and r are going to be. In this case, they're both going to equal to 1/2, so it'll look kind of funny, but this won't always be the case. And then this will simply equal to 3 times 1 plus 1, which is equal to 4. And there we go. We have found the series sum by breaking this big series down into two separate series and then kind of formatting those separate series into series that we have already seen, one being the geometric series and one being the telescoping series. So that's it for today's introduction to series. This is quite an important lesson. It kind of lays the foundation for what series are, and it also goes over two of some of the most important series, the geometric series and the harmonic series. We also discuss convergence and divergence, which is going to be really important in upcoming lessons. So I suggest you go over this lesson a couple of times and maybe you find some practice problems online to solve. Hopefully you guys enjoyed this video and have learned something from it. If this video has helped you out at all, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.